right. All right. Hey, guys. So my name is Gemma. I'm the hardware fabrication lead on T1678.
I'm Devin Castellucci. I'm the fabrication mentor for 1678. Pretty much if it's involving stuff happening in the shop, I have some say or help in making sure it goes smoothly.
Yeah. And this is our mechanical fabrication and prototyping presentation. If you're not here for that, this isn't the room for you. Great. So to start, what is prototyping? Essentially, it's just testing your ideas without like getting a full-fledged mechanism and wasting a lot of time and money and materials. It's really useful if we want to find design improvements without, again, wasting an entire mechanism. And it's super vital for effective and efficient FRC design processes because when you have to build a robot in 6 to 12 weeks, speed is key. Great. So these are just some examples of some of our previous prototypes. This is from 2017 fuel intake with 4-ball shooter. We chose not to do that design, sadly. This is from 2018. If you can see, it is our cube intake. It was
Side grabber.
Side grabber. Oh, wait, that was a side grabber?
Yeah, that was the side grabber prototyping that we did. As you can see, it's just mounted to a kitbot chassis. If you want to do a little bit more advanced prototyping, you can mount your mechanism onto a robot so you can actually see how it performs when it's driving around. You don't need to have it on a fancy drive base. The kitbot chassis does just fine if you need to drive something around.
Yeah. And then lastly, we got our 2019 hatch intake. That one we called our arrowhead intake. And the majority of that mechanism actually did make it onto our final robot. Do you have anything else to say?
No, we'll fill it in as we go.
Great. So what is our prototyping philosophy? It's the same philosophy used for the rest of our team too. If you've seen any of Michael Corsetto's workshops, he says this a lot. It's fail. Yikes. We like fail a lot in the shop, so that way at competition we fail a little bit less, which is nice. Some things that we focus on is experimenting with every scenario, because like when you hit competition, you're gonna have defense, you're gonna like the field's gonna be like a little different than what you have in your shop, and you're not gonna be having like ideal situations. So make sure you're testing out when your prototype will fail. If your prototype works for every situation you've tried, maybe you haven't tried every situation.
Batteries are low. That's the problem. Do we have more batteries?
No, we don't. Just continue with the presentation. Great.
Okay. So, in light of this, one of the biggest things we see a lot of teams do in both practicing
So once we figure out what prototypes we want, what we do is we usually have 5 or 6 different teams depending on how many mechanisms we want on our robot. We might prototype 2 different types of hatch panel intakes, or if we really want 6 different mechanisms on our robot, then we just have one for each different type. We make sure we split our hardware students up into design students, fabrication students, and electrical students. We have predetermined small prototyping groups that have at least one student from each of these sub-teams, to make sure that if a prototype needs pneumatic stuff on it, we don't have to go scramble around for an open electrical student. We've already got one there. There's also a student who's in charge of that prototyping group. So they're in charge of making sure that everything's running on task. They're usually a more veteran member, so they kind of know how this stuff is supposed to be working. And then we also have to document everything we do. So that way, if our prototype is going to make it into our robot, the design team isn't working with just some general ideas. They have exact measurements of what we're doing. And say we don't like one of the changes we made, we have documentation showing us what we need to change to get back to where we were.
So one of the biggest steps we do towards this with our documentation is every time you test your mechanism, someone is taking a video, and then they upload that to where everyone can see it. Because we want to eliminate the whole subjective he said, she said kind of thing where you're playing telephone with, oh, it worked like this. Recording what happened so that you have the ability to analyze it much more in depth. And on top of that, the prototypes that we do, we're always taking as detailed measurements as possible, because let's say you're intaking a ball. The height you have your roller off of the ground is very important in terms of its overall performance. So you need to know that dimension so that once you refine the prototype, you can actually go, okay, CAD people, here is what we got out of this, and actually then CAD up something that is as close to what you prototyped as is possible.
Great. So to get ready for our build season prototypes, we do off-season prototyping, usually in the form of prototyping challenges. So they're short competitions. They usually take about 2 team meetings, which is 5 hours total. And they're given a simple challenge with a limited amount of supplies and restrictions. So they kind of have to and then they have to build a mechanism to fit this challenge. And it kind of introduces the process of prototyping to new members. The groups are set up in a really similar way to the way we do in-season prototyping challenges, or just prototyping in general, I guess. And then we use game objects from previous years because they're sitting in our shop anyway. So we used Stronghold boulders from 2016 to create you had to score a goal 6 feet in the air. So a lot of teams made catapults. We used fuel for a game of Hungry Hippos, which was really fun to watch. And then possibly we're probably going to be using cargo in a future prototyping challenge.
Yep. I mean, it's just, we'll typically dedicate 2 of our team meetings to it. So that's, we generally meet Wednesday and Thursday, 6:30 to 9 p.m. So just over those 2.5 hour meetings, it's okay, you have these 5 hours in order to get this thing working, and then see how well it performs overall. If we're doing something that's more complicated, sometimes we'll stretch it out a little longer. It just depends on what our overall plan and goal is with it. So this is the Hungry Hippos challenge. So basically it was, okay, you have 60 seconds. How many fuel can you pick up out of this area in that time? So some of it is being run off of a drill for running the stuff. This one's actually being run off a motor. They're not actually being driven around under their own power. They have people just sort of pushing them around. So it's a combination of automation components, like the drill to get it spinning, or motors, and just sort of manual stuff, in instance, moving it around. So
The more you rely on people, the quicker you can generally get something to the point in which you can be testing it, but it's not necessarily going to be close enough to the final that it's good enough to go from that and go, okay, now we can just go ahead and design it because we know it's going to be good. Sometimes you can actually get that from a really basic prototype, either as a sanity check against your team's sort of institutional knowledge, what you guys are familiar with making, and go, okay, sanity check, we can make this work. Or, okay, maybe we can make this work, we need to do more prototyping. Or, yeah, this isn't working at all. So it gives you that range so you can narrow down on what you need to focus on to get it doing what you need to next.
Great, and that was the whole presentation. Like, you guys can wait on the class. It's not that. So this is a QR code real quick. It's a feedback form if you guys want to fill it out, giving us ideas on how this presentation was, if there's any future presentations y'all want to see, which would be really cool. But yeah, and now it's like the Q&A session.
I'm going to hit on a few things for how we approach prototypes. So over the years, we have a lot of team members come through and we do a lot of different things with robots. So generally, we'll get a good sense on what we know we can make work and what generally doesn't work. So who here has ever built a scissor lift? That's too many hands. But
prototyping.
So scissor lifts in FRC, I mean, they can work, but they're a huge maintenance nightmare, and getting them to function real well is a pain because of a lot of the forces involved. And just in general, there's a lot of ways that the FRC community has figured out to accomplish most of those goals that work better. So that's one of those things where when we're going through the design process of figuring out potential ways of doing robots, if someone's like, hey, we should make a scissor lift mechanism, we're like, no. We need to find some other way of doing it because we know they're a pain and there's a lot of downsides to them that we don't want to deal with. So we've seen a lot of different ways of manipulating a whole lot of game pieces over the years. And that's one of those things where it can be fantastic to look back at other teams. Be like, okay, this team did amazing with a game piece similar to this. How did they do that? And this is one of those things that's going to be interesting with the not having the bag anymore in the coming seasons is now we have the ability to sort of make much more prodigious use of our withholding allowances as they were, because there isn't a withholding allowance anymore. So teams that see one robot perform terribly well, they go, okay, yeah, let's copy that. And like 4 times out of 5, it does not work the way you expect it to. The reason why is because those teams have gone through a lot of iterations and figured out all the little nuances to work out in order to get it to work how they want. So that's one of those situations where you can then approach it and go, okay, I like how that's working. Let's figure out how we can make this work for us. So you make a prototype of it and go, okay, is it working as well as it is? Sometimes it will, just straight out of it, how you approach it work. But more often than not, you'll have to come up with ways to tweak it in order to get it to perform how it's performing for their robot. And some of them, depending upon how your robot's built, you just can't fit into how your robot's designed. So that's sort of a way to skip through some prototyping steps, is find something you know works and then figure out how it works so that you can then put it into your system. I sort of lost my train of thought, so now we're going to go some questions. So who's got some questions for me?
Where do you put all your videos that your entire team can see them?
It's a Google Drive.
Yeah. So we have a Google Drive that has shared albums. So we split it up into the mechanisms, right?
Oh,
Or is it just one big group?
Mechanisms.
Never really big on
Okay.
documentation.
So we split it up into the mechanisms so you can go back and look at it. And that's also where we'll put logs, like sort of a daily, this is how things went prototyping today. These are what we changed. And these are the dimensions of what we currently have. And that stuff gets updated and edited as we go through the prototyping process. So with that, I mean, sometimes we have some weird game elements. And we'll just go, okay, we need to manipulate this thing, but we don't know how. So let's do 2 or 3 different ways of going about it, and then keep the one that works the best. So there's some iteration that goes on each of those steps, and then just sort of as a team, we would like, yeah, that one's underperforming, can it? And then we take the people that were working on that, and then we distribute them to the other groups until we sort of sort things out to where we want to go. Who's next?
How do you? I heard that you said that you choose the one that outperforms the other one, but if there's 2 that are about the same, how would you choose?
So in situations like that, we will go with the one that we think we can make. Robustness of design is a big one. We want it to not fail in competition. So if there's one that's a little bit flimsier, we'll tend to sort of shunt that one aside. Even if it performs a little bit better, sometimes we'll get rid of that one. So the 2018 top-bottom cube grabber is a good example of this. We did that because we wanted to have a wider acquisition zone, but it ended up coming with some disadvantages that we really didn't want to deal with. It was heavy. It was kind of wobbly with how it was distributed, and ultimately what ended up really pushing it over the edge of getting canned was the fact that it didn't center the cube into a particular location. When you're placing into the scale on auto in 2018, it's critical that you know where it's going to go. And if it's off to one side significantly, that means you might miss that cube and then it's dropped on the floor, which we don't want. All right, who next?
How many different mechanisms are you usually testing at the same time?
I'd say anywhere between 3 and 6. The number usually starts higher and then we work it out. We try and eliminate stuff as quickly as we can. And some of that just comes down to how proficient some of the teams are at just sort of rushing through things to get some answers.
How long does it take to typically make each prototype? To make each prototype?
So the amount of time it takes to make each prototype depends on the complexity of what we're trying to prototype. Our climber this year, we were prototyping probably all the way up to what, week 4 or 5? Because that one's a pretty complicated one. And with something that takes up that much space and resources on a robot's design, you need to make sure that it's going to integrate well with everything so that it works properly.
Also, another question. So when you have those prototypes that take for like weeks on end, how do you make sure that they actually work well? Like your other mechanisms don't interfere with that mechanism.
A lot of careful planning on how we utilize our space. So that's actually the reason why our can grabbers in 2015 were able to work so well, is because we had no idea what the can grabbers really needed to be design-wise. So we just said, okay, straight up the back half of the robot is for can grabbers, nothing else. Everything else can be in the front half, but only the stuff related to the can grabbers can go back there. So we ended up having some can grabbers that were some truly scary monsters. We treated them like a loaded gun, basically. No one was allowed to walk behind the robot after it was loaded. All right.
It looks like you use wood a lot in prototyping. Are
Yeah.
there situations where the other materials work better at the 2 pound, or wood doesn't work so well?
It depends on what you're trying to do with it. Wood, you can use hole saws, spade bits, drills, all kinds of tools that are just real easy to go at into plywood and 2x4s that it would take significantly longer in order to work with in something like aluminum. And that's the primary reason why we work in wood in most of our initial ones. Depending upon how well those initial wood prototypes go, we will either then go, okay, we can definitely make this work. Now we're just going to go straight to our first iteration designing CAD. And for the stuff where we're a little less sure, we'll go, okay, let's make something a little bit more substantial and maybe still use some wood, but also some metal parts, maybe CNC a few components for it. And one of the things that's fantastic about plywood is you can just lay out what you're going to do to it. One really fabulous suggestion. Who here knows about copy-paste machining of parts?
Oh, like legacy parts?
Nah. So you literally CAD a design, and then you print it at 100% scale on your printer, and then you paste it to the part, and then if there's a hole there, you drill on the cross hairs and put that hole there, and then you just cut out all of the lines where they are and trace them. This is how 1678 built our 2012 and 2013 robots. So the 2013 robot was on Einstein. So it doesn't take a crazy amount of resources to get there. Marty. All right, who's next?
How expensive would you say each prototype is?
It's going to vary based on more or less how much it's going into. But the biggest thing with the vast majority of our prototypes is we're only consuming some sheet metal and plywood. Plywood's cheap, sheet metal's not too expensive, and pretty much all of the other components just get recycled back into the stuff that we keep on hand. And that's another thing is before build season kicks off, it's really valuable to just say, if you guys like using versaplanetaries, build up a bunch of versaplanetaries that are already wired and ready to go, so you can just immediately start testing with them. Because drills are great for sort of the initial testing and getting the sanity check, but they only go so fast, and their torque is going to be different than how the actual motors we use in FRC are going to handle. So you just need to keep that in mind when you're doing testing. Like, is this really going to be important, or are you already familiar enough with how a motor is going to handle between how a drill handles?
So say our team doesn't really do that kind of prototyping. What are some things that, like, if my team hasn't done that, what are some things that you can give, like, tips and tricks?
So just try doing some prototyping real quickly in the off season is really sort of the best advice, because you need to have your members be practiced at prototyping for them to prototype well and quickly. Other than that, a lot of the prototyping that we do is it's just hand tools. So knowing how to use a drill effectively, knowing how to drive a screw in, knowing how to use hand saws, jigsaw, all that, and just sort of knowing how to apply those tools to the process that you are generally going to be going through during the season for generating those prototypes.
When you set up when you're doing your prototypes, do you set up like a full electronics board with like a Rio and everything, or do you just like hook them up directly to batteries or something?
Initially, we'll definitely go more than just plug it straight into a battery routine. Now, the one thing that doesn't work very well for is shooters, because most shooters need to actually have proper control system loops so that they're performing how they actually will on a robot. Because when you're doing a shooter, you want it to be roughly sitting at the peak power curve on the motor, which is about half speed. But if you're just plugging it into a motor, it's just going to go all the way up to free speed, and that's not going to be an accurate test for you. There's some sneaky ways you can take one of the motor controllers and then just make a really basic circuit that you can hook a potentiometer up to, so you can at least tune speed. But anything more than that, you're going to need to start actually hooking it into the proper electronic systems. So it's just going to be a demand based on what you're trying to get from it. If you feel, okay, we actually need to have some programming behind this thing to effectively test it, you need to go ahead and go through that step.
So, wait, you said that shooters are supposed to go to what did you say?
Peak power. So,
like on the Vex shard.
yeah, so you can go on to Vex. They have all the motor curves for all the motors we use in FRC. And so there's a number of different spots. So there's the efficiency, torque, voltage, and power. So the power is the power out. And that's generally highest right in the middle of its where its free speed is. So let's say you're using a 775, its peak power output is going to be at about 9,000 RPM. So if you're designing a shooter, you want to design it for somewhere in the range of that 8 to 10,000 RPM range is what you want that motor going for the target speed the shooter wheel should be spinning at. The reason why is that way it can get the most energy back into the system the quickest. So every time you shoot a ball through it, it can then ramp it right back up to the speed it's supposed to be sitting at. So it can then shoot more consistently every time you feed something through it. And then if you're just wanting something to run constantly all the time, and you're not taking a bunch of energy out of it, you can push it towards the higher end of the free speed where it's more efficient energy-wise. Yeah, something more like a roller. Because the speed isn't as important once you actually get the thing. And then that you just sort of design where you're going to put the stall. So.
You set deadlines for your prototyping teams?
Yes, we do. Don't always hit them, but we certainly try. So one of the things we try and do is we try and have our drivetrain designed by sort of the middle of the first week at the latest. So by the time it's the second weekend, we can have all the manufacturing that we can just start plugging away at it so that we can start assembling it at the end of week 2 and then get everything together. I might have it shifted back slightly. It might actually be, we want to do a week earlier. You remember?
No, not really.
Generally, we try to have something by the second weekend or by the end of the second weekend. But for a lot of prototypes, especially for complicated stuff like climbing and stuff like that, those prototypes will run later into the season. So we aim to have most of them done by the end of the second week, but lots of them will run later.
The goal that we're really driving to hit during our build season is sort of by the end of week 4, we have a mostly functioning robot that is programmed and able to drive around and start doing some practice. And then continue improving it until it's competition worthy. All right, let's get some more questions. Yeah.
Do you guys fit your manipulators to your drive base or your drive base to your manipulators?
We fit the manipulators to the drive base unless there is some very specific reason we need to do it the other way around. So 2015 is a good example of, yeah, the drive base was definitely driven by the fact you have to intake totes into the dang thing. But most of the other years, It's just straight up rectangular West Coast drive base, no holes cut into the drive frame. And then we just have something that will come out to suck it into it. Sometimes the drive base dimensions will get modified by the fact that we have to bring a ball in through a gap in the bumpers. That's definitely a lot more typical for us. Let's see here. 2017, robot did have a cutout in the drivetrain, but that's because of how the rules worked. You couldn't have something come out very far, and that made it a major pain to try and have an over the bumper intake. So we just opted to have it suck something in through a gap and then feed it up into the hopper. And it's basically just, do we need a cutout in the front of the frame or not?
Yeah, our drivetrains, especially for the past like 4 or 5 years, have been so copy paste that they're generally done before the second weekend. Like we determine, do we want to go wide, do we want to go long? And then from there, we determine, do we need the cutout or not? If not, it's standard West Coast drive, and then we just build on top of there.
Thank you. All right. More questions?
With no bag and tag, what do you think that's going to change next year?
Absolutely nothing for us.
Absolutely nothing?
Pretty much. Well, I mean, it'll be nice being able to get to work on the competition robot in between events and leading up to our first events. But that's basically the only change. We're still going to be building 3 robots. One of the reasons we build 3 robots is because we have a lot of students. And it really helps when you try and make 3x the quantity of everything you actually need. And you're like, okay, these ones are the best. Those go on the comp bot. And that's one of the primary filters we do for what goes on comp bot versus practice bots. The practice bot parts are generally not as tight to the tolerances that we have. Yeah.
So when you're making your robots, do you do them all at the same time?
We do them all at the same time, or at least as much as we can. With stuff where we're like, okay, we want to do a first iteration of this mechanism to see if it's working well enough, and then we'll do quantity 1 of something in order to get it out, put it together, test it on the robot, and we'll go, okay, yeah, we like that. Build the other 2. Or if it's something that we're like, yeah, for like the drivetrains, build all 3 at once. Go for it. And that's really critical to sort of take that step where you're building everything as much at the same time as possible, because machine setup time is a very significant portion of the overall machining process. So if you're setting it up twice because you're doing 2 robots, you're losing a lot of time versus just setting it up once and doing it all in one go. Batching is always more preferable, at least for me. That's why we do that. So
within your deadlines for your prototypes, about how much time do you spend at like the whiteboard versus just going at it by eye?
A lot of that depends on sort of our institutional knowledge behind it. So that's one of the reasons you'll see us do different stuff in the off season. The reason we're doing different stuff is because we haven't done it before. And off season is the best time to approach new ideas because you have the penalty for failure in the off season is very small. Off season events are very cheap, and you're less hard pressed for getting something sort of hammered out by a very hard deadline. And so in the past, this has included doing an articulated arm, doing an elevator. We did a turret with a pneumatic catapult. That one scored 1 goal.
50% accuracy rate.
Huh?
50% accuracy rate.
This,
It shot twice.
Oh, yeah.
Once. It's really good.
That one was also really tiny, so we learned a lot on space packaging. So it's just try new things in the off season so that you learn from them, and particularly it's really valuable because it exposes your students to those systems. For those of you that are mentors in here or veteran students, you want to have your newer students get exposed to these designs so that they have some experience with them, so that they're more familiar with it. So come build season, it's way easier for them to just sort of take it and run and succeed quickly at it.
So you mentioned institutional knowledge. I'm just curious, I know it's fabrication, but how do you do the discipline where you're documenting stuff and people are reading it, or are you relying on getting hands-on experience and they're there for 4 years and you can bring that knowledge?
Mostly the second one. For the other part of that, we generally just rely on, okay, what other robots have been successful, look at them and go, okay, do we think we can relatively easily replicate that, or do we think we need to play around with that in order to figure out why they have it working so well? So that's more the prototyping. Let's go with some more fabrication related stuff now. So I have done a lot of weird stuff over the years in order to make robots with 1678, and there's a lot of stuff up here to pick my brain about if you're wondering how we sort of go through the process of making stuff.
Where do you generally put electrical boards and stuff like that on your robot?
Almost always the bottom. Generally, we just throw them on the belly pan and call it a day. We plan out the layout as early as we can based on where we're thinking mechanisms are going to be. If there's anything where we're intaking and manipulating a bunch of stuff down low, it can make that process a real pain because we're not 100% sure as early as we'd like necessarily. I mean, just in general, every single thing you can put at the bottom of your robot is good. That's another thing. So 1/8" wall tubing. Use it in the drivetrain. Don't use it anywhere else unless it's breaking. 16th wall is almost always good enough. And the primary reason for that is it doesn't seem like it adds up that quickly, but it really does. Particularly if you're doing something like an elevator. One, your elevator is going to be heavier, but two, now you have a whole bunch of weight that's going up real high, moving your center of gravity way off the floor, making you far more likely to tip. Everything you can do to put more of the weight down at the bottom, less tipping. Less tipping, less sadness. All right. What else? Yeah.
So do you keep all your electronics on the belly pan, or do you like move some of them up?
Some of them get distributed. So our radio and some of our there's a few speed controllers. Yeah. With stuff like on elevators, it's actually more advantageous to put the speed controller closer to the motor. It's a little bit more power efficient. And generally, the speed controllers we use these days don't weigh that much, and they're nice form factors. But radio stuff is generally nice to not have down low, so you can get at it. So it's easy to plug in your laptop, and you can look at the blinky lights easy. You have another one?
Yeah, I was wondering, how much funding do you guys usually have for your robot to start off with?
I don't actually know what our split is on the robots.
Like, is usually most of your prototype stuff just essential because you have a lot of funding, or is it like 2.5?
Honestly, the prototyping costs aren't usually that much. Sometimes, like if we're doing carbon fiber forks for the 3-robot lift, that gets pretty expensive pretty quick because carbon fiber is not cheap, but that's an extreme outlier for the vast majority of teams. I mean, like disposable stuff that we just burn through because it's the parts afterwards aren't going to be reusable in the first couple weeks is probably only in the hundreds of dollars. I mean, a 4x8 sheet of plywood is generally 20 to 50 bucks, depending upon what the plywood is. And you can do a lot with that plywood for building prototypes. And the rest of it's just finding creative ways to make the process not cost much. But like with us, we had a whole bunch of versaplanetary stuff. Some of it was did by my work, and that's one of the reasons we have so much of it. So having stuff like that on hand can definitely be expensive, and that can be something where you bring up, okay, how much do we want to budget to just having a bunch of these parts around so we have them to play with when build season comes out. And that's up to sort of how you want to approach your prototyping session in build season. There's a lot of different ways to do it. One of the things that's real nice to have is just, okay, let's throw everything on 1/2-inch shafts. Let's have the bearings we need for it and the shafts on hand. Have it be, okay, we have this pile of 1/2-inch shafts. Don't bend them. Don't cut them down unless there is a very good reason. Because cutting shafts down to size is one of the quickest ways to go through a lot of money in prototyping. We use a lot of shafts. There's a lot of roller intakes. And just, they're great for so many things. It's just be like, okay, don't cut it unless you absolutely have to, because they cost money. And it's one of those things where it's like, after you're done with it, you can take all the stuff off of it, and now you still have the useful shaft that can be used for making roadwell parts.
Any rules of thumb for using pneumatics versus electrical motors in your mechanisms?
Pneumatics are fabulous if you just have something that's like, okay, it needs to be in this position or this position. Anytime you have that situation, pneumatics is really nice. The other thing is, okay, am I going to be able to get something where I have sufficient mechanical advantage to actually set up a linkage for this thing to work? Some of that you can cheat by using stuff like surgical tubing or gas shocks in order to bias it so that the piston doesn't necessarily have to crank really hard to pull it up, whereas it just needs to give it a slight push to hold it down. If it takes a lot to get up and it only needs a little bit to keep it down, that means you can just have one piston that's balanced in each direction, and then you just have it sprung back. So it's fighting it to come up, so it doesn't have to put as much effort into it. And then the amount of effort it puts to push it down is at least approximately the same. But other than that, it's going to depend on what you're trying to do with it. I mean, pneumatics aren't going to do you much good in rotary situations. So if you have rotary, you're going to need the pneumatics. And then the only other thing that you want to look at is, okay, does this mechanism need to have more than the 2 positions, or is there a chance where it seems worth it enough to design it to be using a gearbox in order to position itself? The downside of that is if you're going to do it that way with a motor, now you have to definitely throw sensors onto it so that it can actually keep track of where it is, so it can stop at the proper location for, say, a medium position stop. Who else?
What kind of pointers would you give a team who hasn't ever done anything with any kind of suction manipulation to kind of give them a head start, kind of like the don'ts, so that way they don't have to go through that whole process?
Generally, don't do suction. So honestly, I'm quite amazed that so many teams managed to make it work real well this year. And the teams that did make it work well, I can guarantee you they spent a heck of a lot of time making it work that well. So my personal opinion is try and find a way to do it otherwise. So suction, depending on how, if you can manage to find something that generates suction and you can shove a 70 or 775 into it, then it's a lot more viable. If it, don't use the Venturis generally. They can generate really good vacuums, but they take a lot of air to run. And the air generation of the compressors that we use in FRC is not fabulous. and their duty cycle is definitely not great. So try to avoid suction, but if you really want to do it, just know that it's probably going to take you a considerable amount of time to make it work properly. And generally, with suction, only consider it if you've got some really nice, hard, flat surfaces. Getting it to conform to and make contact with anything that's got any kind of curvature is a real pain. So that, and also texture makes it really hard. Yeah. All right. More questions?
How many people do you usually have for prototyping specifically, like on each prototype?
It's 4 to 6 generally. So one of those people will be one of our electrical students, and that's just so that we have the necessary experience for any wiring of motors into it that needs to happen, or just the pneumatics knowledge in general for doing pneumatic pistons on the prototype. So we'll have a mentor that's sort of helping advise the whole process of that prototype team. We have a student leader that's sort of in charge of managing all of the work that's happening on it. And then we have some mechanical students and then an electrical student that are there to focus on it. And if we had to do something like a shooter prototype, we'd have one of our programmers that would be tasked to sort of help program anything they needed for it. They wouldn't be doing that full time, but they'd sort of be set aside as the person that they go to for it. Let's go with some more questions.
So on your guys' router, what is the one thing you couldn't live without?
Routers. Routers are amazing. I'm just going to put that out. Who here does not know about my router mega thread? Raise your hands. Okay. Chief Delphi. CNC routers for FRC robotics. Just throw that in the search thing. It's last I checked, almost 600 posts long, and it is absolutely chock full of information from all different types of routers that teams use. The feeds and speeds, 1678 is on there. You just have to run a search through it, and it'll pull up the link to the file. And just in general, it's a huge resource that the community has been using for years. At this point, it still makes me happy seeing people post to it. But so some of the biggest things with routers operation is, how are you zeroing your tools? What are you doing to evacuate your chips? And what are you doing to keep your bits from getting stuck in your material? So sort of the biggest thing is, I was very skeptical of the sort of touch contact zeroing tools, but now that we've actually been using them for a couple of years, I'd really suggest them. They're a little bit of a pain to get set up with a Velox machine. If you have a Velox machine and you want to know how to set one up, bug me. I will take some pictures of how we spliced into the control box. Basically what we did is, the CNC has limit switches for its axes. We basically just plugged it into the x-axis 0 switch for that. And so the only problem that happens is if you accidentally make contact with the alligator clip and the 0 surface while you're trying to home the machine, it's going to go, oh, hey, I'm touching the thing. I can stop now. This is home, which it's not. But that's pretty easy to avoid. So that just makes the whole process of zeroing the tools really easy. You just always have a standard of, are you zeroing to the top of your material or to the bottom of your material? On 1678, we always zero to the bottom of the material. That way it is always the same. And that is just critical to always keep the process the same so people don't accidentally mess it up because it's, oh, this is the only way we do it. We don't do it any other way. The other stuff we have on there, so chip evacuation is a huge thing. If you have chips piling up in your cut, it is going to get hot, and then the chips are going to get gummy, and they're going to gum up your bit, and that bit is going to either break or start producing garbage parts. Generally, it's going to produce garbage parts until it breaks. So the biggest things is fewer flutes is better chip evacuation. So single flute end mills are awesome for that. Next thing is a whole bunch of airflow aimed right at the bit to blow chips out. And then the next bit is, okay, how can we get a little bit of lubrication in there? So what we do is we use an automotive fuel pump that circulates in a line in order, so it just has a little bit of pressure, and then we use a precision needle valve to let some WD-40 into it's a $15 mister off Amazon. The problem with the misters themselves is if that's all you're using to regulate the amount of oil or whatever lubricant you have, they are incredibly touchy and they're a pain to set up. But using the fuel pump, it has a constant back pressure at all time. Doesn't matter where the oil level is. The oil could be on the ground, it could be 10 feet up, doesn't matter. It's going to keep the same amount of pressure. And then you're just tuning it so it's allowed to bypass the needle valve sort of at a set rate. And that allows you to get just the tiniest hint of lubrication. It requires very, very little to properly lubricate a cut. And if you have not been using a lubricant in your CNC router experiences and you switch to it, it is a world of difference. You can go so much faster, you'll get cleaner cuts, and your bits will last much longer. And then the other thing is Lockline sells vacuum hose size, like posable hose. It's a little pricey, but you only need it to go sort of off of the router head itself down to where the bit is. And then we have that run to a shop vac in order to, at the very least, take a bunch of the chips away. The aluminum chips are really heavy, so they tend to still fly off. But at the very least, when you're cutting through sacrifice material a little bit, you're generating wood dust, and it's real nice to get that all sucked off. And tube jigs are another that's a subject I can get into some pretty extreme detail with. So if you really want to pick my brain about that, come see me either tomorrow and just pick my brain on the various ways you go about doing that. So we have toolmaker vices on our Vellox CNC router, so that's great for doing long, larger tubes. And then the Omeo router, we have 3 tube magic jigs set up on it. So we can do 3 tubes at the same time, and it will just go through them. It'll only do up to about, like, I think 35 inches. But that is still what we use to make our elevator rails, and those are like 5 foot. The way we pulled that off is you're already drilling a hole pattern in it, so you know where the holes are. So you then just need to use one of those holes and shift the whole thing down, and then have we use a dowel pin in order to locate those holes so that it can then continue doing the rest of the machining. And that's worked out really well. All right. Next.
During the prototyping process, what differences would you see between the rookie team and veteran teams?
Mostly the veteran teams have a heck of a lot more stuff laying around. Other than that, the process really shouldn't be that different. Basically, the veteran team can generally sort of just go for it a little bit faster because they'll have something lying around that they can just sort of grab off the shelf, throw it together, and then get it going. Whereas rookie teams generally have to go on a scavenger hunt to the hardware store and be like, okay, what do we have here that we can make work to see how this prototype's going to go? Definitely as a rookie team, I wouldn't say go out and buy a whole bunch of stuff until you really settle on what your build style is going to be. So 1678's build style is thin wall, aluminum extrusion tubing, with a whole bunch of regular hole pattern on it, sheet metal plates, and sort of figure out everything else from that. But I mean, our robots are tubes with holes and sheets with holes and riveted together. And that's pretty much our entire robots. There's only a very short list of other stuff on our robot, like the various 3D printed components. And I mean, honestly, the main reason we 3D printed is because it's often faster than just ordering. And we have the Markforged printers, which are really nice. They just work. I, for the longest time, actually really was against using 3D printing in FRC applications, but I've definitely come around on that now that I've been working with the Markforged. I have one at work. They're amazing. They actually print parts instead of part-shaped objects. Whereas a lot of the printers you have for most FRC teams, where it's printing PLA, and those, they're good for like electronics mounts, stuff that's under low loads, and just print all the spacers. They're amazing for printing off spacers because you just get it the size. You don't have to worry about making up drawings and getting it all the same dimension. And just push button, come back a day later, receive widget. They're real nice for that kind of thing. All right.
What's the best way to research potential mechanisms that have worked for other teams in the past?
Look up previous year's games and sort of what they entailed, and then from there just go on the Blue Alliance and then start looking at teams that have done really, really well in those particular years. Basically, okay, did they do really well in their division at Champs? Did they win their division? Did they make it to Einstein? And you can just sort of parse through it that way. It's generally quick. And then if you have a bunch of kids on your team and you can get them like, yeah, look at all these robots from these previous years, and just sort of let them loose on the various forms and whatnot, to just what other stuff is out there. And that's one of the things that's interesting is you can be really good at designing things, and someone can then show you one thing and you're like, how did I not know this was a thing for years? It was like that for me when I was shown PEM nuts. So it's just an insert nut that gets pressed into a piece of sheet metal, and now that piece of sheet metal has an attached nut to it. And I never knew that that was a thing you could do. And now we don't use them very often, but they're dang handy when we want that kind of solution. If you have a part that's really hard to get a wrench at, you put a PEM nut on it, and now it just has the nut on the part that, let's say it's 16th inch aluminum, you're not going to be able to thread that and actually have it hold anything. But you put a PEM nut in that, and now you can crank down on it and get some serious clamping forces with it. And it's just, the more you can expose yourself to the different ways there are of doing things, the deeper your knowledge base of what's out there to find an answer to the solution you're looking for. And just the more you know, the more you can do. And that's just always been a fascination with me, is learning all of the different things that's out there. And that's one of the reasons why I'm the fabrication mentor, is because I know how to do some really bizarre things that are way outside of what the team normally does, but they're like, okay, we want to do blah, blah, blah. And I'm like, oh, yeah, we can do it this way. They're like, what way? I'm like, this. And then I help the team figure out how to do the thing, and there we go. So, like our flywheel for our 2017 robot was a 6-inch OD by 5-inch ID bronze tube that was heat shrunk onto an aluminum hub. So the flywheel weight was 1.25 pounds. The bronze ring around the outside was a full pound of that 1.25 pounds. The aluminum was not dished in any further. It was the same width. So now you have something that has an incredibly high moment of inertia for a rather reasonable amount of weight. And then on top of that, you gear it up so it goes faster than the actual shooter. Now it's holding a heck of a lot of extra energy to sort of buffer out the sending a whole bunch of fuel balls through it. So it's far more consistent in its shot accuracy. And if someone else had been like, hey, we want to do this thing, no one on the team would have known how to properly really approach that task. I just pick up various bits of knowledge over the years, and I'm like, okay, why not do this? It's also why we did the cheese grater thing last year. Yeah, so that only happened because I was really gung-ho about that. I was doing a lot of support on the students in order to get it to come out the way it needed to, so that the holes were the correct spacings. The die would have enough space so we could form the flanges into it. And then just the general assembly process was really involved, because when you do that, it tends to warp it enough that it's sort of a pain to put it together. And if you put it together in sort of a lazy fashion where you're not like really trying to make everything line up properly, you'll end up reducing the overall effectiveness, because now the holes are a lot easier to get wallowed out, and it's going to lose stiffness over the time. So that one ramp made it through all 3 regionals and champs. And the only detriment we had at the end of all of that is it had a slight depression on the outer edge from people's wheels running over it and slamming into it. And I mean, we did a lot of climbs with that thing. And that ramp was 25 thousandths of an inch thick.
25.
Yeah, 25,000.
Okay, that's pretty thin.
It's about as thick as probably an index card.
Yeah.
And that overall ramp, not including the brushes, was 8 pounds. And if that would have taken a lot of time for the students to sort of approach and try and develop that solution, but because I had some knowledge base behind it, I was like, okay, if we go about it this way, we can make it work. So we can skip a bunch of those trying to figure it out steps. And that's what having larger knowledge of what's out there is really useful for, is you can skip some of that stuff because you already, at the very least, know where to look for the information to find out more on how to do it. And that's what having people go out and look at other robots that have done things over the years is really valuable. Any other questions before we wrap up? No? Really? Yeah.
How do you utilize laser cutters?
So previously, it's just a laser cutter I had at work. And our team basically didn't do anything with that. We just got a laser cutter, and we managed to fit it through a 32-inch wide door. And some disassembly was required on that. That was an interesting and annoying process to get it into that room. But it's the only place we had space. We accidentally bought that one. We were like, yeah, let's get this laser. And they were like, nah, we don't have the space, so we'll not get it. But that didn't quite make it through the school district's grant thing, so it ended up getting bought. And one day this crate shows up, and we're like, oh, what's this? Oh, it has my name on it. Oh, it's from Boss Laser. Oh, dang it. But so we just got that up and running literally last weekend. So we'll see. We're definitely going to use it a lot with prototyping because 1/4-inch Baltic birch is fantastic for prototyping. It's generally fairly cheap and it's really strong and easy to laser. Who's the other person?
Yeah, so I noticed that you said that you do some of your tubing on your CNC routers. Is there any reason that you do on the routers instead of the mill?
We usually get less scrapped parts that way.
Really?
So it's kind of a shortcut for just throwing more material at it in the early season so they get enough time on the machines in order to make good parts.
Okay.
I mean, it depends on what we're doing. Sometimes when it comes down to crunch time and we just aren't able to get enough cranks through the router, we totally rely on our mills to get the volume through. But we generally try and do the smaller pieces. All right. Now, I notice you've been recording the sound, right?
The entire thing.
Good. So make sure you get that to our guys so we can try and sync the audio to this.
Also, if you had any more questions that Devin didn't answer, this is the general hardware.
And this is my email.
Yeah. So you guys can email them and we'll respond.
Signing off. That's nice.